Good morning. Welcome back. What are the three big questions in machine learning? In approaching any new machine learning framework, algorithm, trick, buzzword? Same questions to be asked about decision trees, neural networks, regression, linear regression, that is, deep learning, SVMs, graphical models, hidden Markov models. Okay.
Hard bias?
Hard bias. First question is what's the hard bias? What's the hard bias? Also, what's the expressive power? Expressive power. It's kind of the same thing. The expressive power of a framework or of a formalism is the kind of solutions that it can represent in principle. If you decide on linear regression, then you can only express linear functions. If you decide on quadratic regression, you can only represent quadratic things. If you decide on decision trees, you can only represent whatever decision trees can represent. We found out last time that they can represent any classification on discrete variables. But if you decide on decision trees that are smaller than 100 nodes, then there's a limit to what they can represent. And that's true for just about anything we do. Expressive power sounds like the more is better, right? Who doesn't want to have good expressive power? But that's not quite right. More expressive power is not necessarily better. More expressive power means less bias, less hard bias. Being able to express everything is not a blessing. It's a curse. Or at least it's not a blessing. So we have other names for hard bias. It's language bias, representation bias. Another way you can think about the same thing is, what is the hypothesis space? What is the hypothesis space? All right, question number 2. What's question number 2 we need to ask? Yes?
Soft bias.
Soft bias. Okay. Given what you can represent, do you treat all possible solutions within that space equally, or do you prefer some to others? You can prefer, one way to prefer some to others is by ranking them, and then looking for the highest ranking member of your space that still agrees with the data. A slightly more sophisticated way is to assign each member of your space a prior degree of how much you like them or how much you think they're likely to be the right solution. So you encode your prior preferences numerically, maybe in a distribution, maybe just in scores. So that's kind of like ranking, but you don't have to explicitly rank every one of them. You just assign them a number. So by soft bias, we sometimes call it preference bias. Rank bias. Or the other approach of assigning everything a priori belief or a priori preference as a number, you can think of as putting a prior over your hypothesis. Over H, your hypothesis space. And then, what's the third question? Yeah?
Is it efficient?
I'm sorry?
Is it efficient?
Is what efficient?
Our method for selecting.
Our method. So you're implying there's a method there for selecting. Yeah, so the third question is about that method. So I call it the search problem. or the algorithmic problem. Given that you restricted yourself to a particular hypothesis space and that you assigned relative preferences to members of that space, and given some training data, how do you combine the two together to come up with a single member of the space? Okay? The simplest example would be if you have a rank bias. How do you find the highest ranking member of H that is consistent with the data? If you're willing to allow some inconsistency with the data, maybe you weigh together how well it fits the data and how simple it is or how high it is in your ranking. How do you, once you decide on the formula for combining them, how do you find the one member that optimizes that combination? So I'll call it, how do I search H for a particular member that optimizes what does it have to optimize in the most general case?
Error.
Error, so minimizing the error over the training data. All right, let me not write it down yet. If I want to take a more sort of I don't call it balanced approach, but if I want to take into account both my prior or my rank or my preference over the members of H with how well they fit the data, then I want to optimize a sum of two things, which I hinted at the end of the last lecture. I want to optimize how well H fits the data and the second thing I want to optimize is some measure from here. If I express it as a rank, I want something that's high, ranked as high as possible. If I express it as a prior, I want something that has the highest prior. I'll call it prior preference. The soft bias measure. Whatever it is that we use as a soft bias measure. Now these are very different things, and they're often measured in different units. So we will need, part of what you need to do is to decide on how you combine them. Do you care more about this? Do you care more about that? Let's take a concrete example of decision trees. We decided that the soft bias for decision trees is going to be the number of nodes in the tree, right? So let me write above it here the example of decision trees. The hard bias of decision trees is none. No hard bias in decision trees when used to classify discrete valued attributes. Soft bias we decided on is number of nodes. And the measure of how well it fits the data, we could simply, since we're talking about binary classification in our example, we can talk about how many of the training examples it got correct. Let me reverse that. Let's say percentage error on the training data plus some measure of the number of nodes. we want the overall sum to be as small as possible. We want the percent error to be as low as possible. We want the number of nodes to be as low as possible. If you have two candidate trees, one of them has 100 nodes and makes no mistakes, and the other one makes a single mistake out of, let's say, thousands of training examples, but has only 3 nodes, you might prefer that, right? But how do you weigh the percentage error versus number of nodes? Well, we don't know how to do that, so we will weigh it with the parameter. So we will put a lambda here, and a 1 minus lambda here. And lambda now becomes our knob that allows us to trade off degree of fit to the data versus simplicity of solution. This is maybe one of the 2 or 3 fundamental ideas of machine learning. Explicitly tuning or viewing learning as finding a trade-off between simplicity and fit to the data. If you think about it, this is what science does all the time. Science, like physics and chemistry and other softer sciences like biology, what they do a lot of the time is come up with models. What are models? Models are simplifications of reality. They're stories we tell about reality that we know are not true, but that we think are pretty close to true. That they're a good description of the data, not perfect description of the world, but good descriptions of the world, but they're very simple. And the theory is considered better, a model is considered better, if it is very simple, it explains the world better. It's the same thing here. Simplicity and degree of fit. This part is usually called the loss. The simplest case of loss is percent error. This part is often called the regularizer because it's there to regularize the solution. By regularize meaning making it less complicated, less ornate, simpler. And the two together could be called regularized loss. I gave you an example of trying to fit a polynomial last time. We had a polynomial, we had a couple of data points, and we decided to try to fit a line to go through them. How would you decide on what degree polynomial to fit through here? We said that with 5 data points, we can fit perfectly a 4th degree polynomial. Let's say we consider a 2nd degree polynomial. It might look something like this. Here's the error. We first need to decide on the loss function. Let us assume that the loss we choose would be the sum of squared errors between yi and f of xi. N is 5 degrees of freedom. Or maybe it'll be the average squared error, 1 over n. Why do we use squared error? We don't have to. We could use any other measure, and it would lead to different answers, right? So we have a choice, and it's up to us, and we have to think about what loss function to use. But let's say we use this squared error. What would be our measure of simplicity? The degree of the polynomial, right? So we're trying to minimize is a loss plus the degree of the polynomial. Now there's a lambda here. What should this lambda be? One way of deriving a lambda value is by using held out data. You can do it here or here, but here with 5 data points, it's going to be a little tricky. Another way to derive a lambda value is through theoretical considerations if you know something about the family of models you're considering. So there are particular solutions in statistical theory when the set of models that you are considering form a hierarchy. You think about degree 0 polynomials, that means all horizontal lines. Degree 1 polynomials, these are all straight lines of any orientation. Degree 2 polynomials are all parabolas, and so forth. This is a model hierarchy. When you're selecting from a model hierarchy, you have the added advantage that you know it's a hierarchy. You know that every member of the simpler family is also a member of the larger family. This is true also with trees if you consider the number of nodes as your measure of simplicity. If you're allowing trees with 37 nodes, they include in them all trees of fewer nodes. When you're in that situation, you can say something theoretical about how much better fit do you expect by having more degrees of freedom. And you can take that into account, and it gives you an answer to what to put here, more or less. Other times, you just need to count the number of free parameters that you have. And in statistics, again, there are 2 main methods for deciding on the conversion factor or exchange rate here. You can think of this lambda as an exchange rate between simplicity and goodness of fit. Okay? And often you will use lambda 1 minus lambda if there were probability distributions, they had to sum to 1. Otherwise, you would just find the lambda there. It's just a conversion rate. You know, dollars to marks, euros, yuans. I want to mention the 2 methods that I described before in statistics. They're called AIC and BIC. You may come across them. They're both alternative methods for deciding on the conversion factor when the way you measure simplicity is by number of parameters. So this would apply to polynomials, but it would apply to many other models, including non-hierarchical models, families that are not necessarily hierarchical. The more parameters you have, the more you can expect your model to find a model that would fit the data better, even if the underlying data did not come from anything like that model. In general, if you have more parameters, you can overfit more, right? AIC and BIC try to take that into account. They're different formula. They lead to somewhat different value of lambda. AIC effectively tries to maximize your predictive power. So it is equivalent to deciding on the value of lambda through cross-validation. It pretty much does that. BIC, standing for Bayes Information Criteria, doesn't quite do that. What it tries to do is to maximize your explanatory power on your training data, to simplify the explanation, use the minimal number of parameters that would still explain the data. So you can think of BIC as looking back and doing the best job of explaining, and the AIC is looking forward and trying to do the best job of predicting. As a result, BIC tends to end up with solutions that are simpler in the sense that they have fewer parameters than AIC. AIC, in a way, doesn't care so much how complicated your solution is. What it cares mostly about is how well will you predict the next data point. So for us, machine learning types are come to statistics from the outside. We recognize AIC is kind of what we've been caring about mostly. We care about performance. We care less about explaining. Right? I mean, that's just historical, cultural factor. You can care about whatever you want. But typically, in machine learning, people have done cross-validation because it's perhaps the most direct way of trying to maximize performance on future data. And this is equivalent to AIC. Question here?
Oh, yeah. So for AIC, you use held-out data, right, to do the cross-validation? Is that right?
Implicitly, you do. The formula, it's not an algorithm that uses held-out data. It's a formula that tells you how to weigh number of parameters versus degree of fit. But it's equivalent to leave one out. Yeah.
So what is cross-validation?
What is cross-validation? Thank you. I use the term without defining it. So here's all the data you have. If you fit your model based on all the data you have, and you then test it on the data itself, that would not be a fair test, right? Because the model has been exposed to this data. You could say it would overfit to it. A simple-minded solution is to leave out some of the data up to here, train on this part, and test your model on this part to try to get an objective measure of how well your solution would work on future data. So this is what you pretend is your future data. Okay? The problem with this approach is that you've now trained on only, say, 70% of your data, as opposed to on all your data, and you only tested on a relatively small amount of data, 30% of the data. So you don't get to test on everything, so your sample is smaller, and you don't get to train on anything, so your model is not as good as it could be. Ideally, you want to train on everything and test on everything. But you can't do that at the same time, because then the test data is not independent from the training data. Your estimate of how well you'll do in the future is going to be biased low. You're going to appear to be doing better than you actually will in the future. So the very common solution for that is to leave only a small part out as your test set. So now we switch from 70% to, say, 95%. So we solve this problem almost completely. You train on this part, you test on this part. And now you say, well, this is so small, it's a very small sample, we don't want to rely on it as a measure. Okay, remember the error that you got on this part. Now repeat the process, but this time exclude not this part, but this part. So now you train on the 95% that excludes this 5%, and you test on this 5%. Every time you repeat this process, so here you have error 2, and now you move the next slice, and you repeat that 20 times. You train 20 different models, each one on a somewhat different 95% of the data, and each one of these models is tested on the remaining 5% of the data. And now you take all of the 20 error numbers and you average them. So now you achieved almost completely both of the goals. You are training models that are trained on almost the entire data, 95% rather than 70, and you're getting a test estimation that is based on data that was not used in training and yet is based on the entire set, so it's robust. If you don't like 95%, if you want to go to 99%, then you split your data into 100 fractions. In the limit, you take out one data element at a time, train your model on the remaining data, so it could be 1,000,000 minus 1, test on a single data point, throw that data point back in, take out a different data point, retrain your model, test on this one, and so forth. So the 5% could become tiny, tiny percent. A couple of caveats. One of them is that it's computationally expensive. What I showed you here will take 20 times as long to train because you have to train 20 different models. If you go to the extreme of taking out one data point at a time, then you have to train your model as many times as there are data points. That could be very expensive. The second caveat is that if there are dependencies in your training data, then you need to be careful to take out not a single data point, but a whole chunk of data that is interdependent. You want to make sure that every time you train something and test on something else, that stuff you test on is independent of the stuff you trained on. So if your data comes from, say, a time sequence, and you suspect that there are dependencies within successive time points, then you don't want to take out a single data point. Maybe you want to take out a large chunk at a time. When you do this, this is called cross-validation, because you validate or you test your model by taking out data and checking it on that left out data. When you take this to an extreme and you take out one data point at a time, it's also known as leave one out. And you had a question.
So at the end you have a single error metric, but you still have 20 models.
I forgot to mention. Going back to the example of 20 times 95%, 5%. Now you take all 100 data points, all 100% of your data, and you train one big model. You don't test it anymore, but you have reason to think that it's at least as good as the average error you calculated. Yeah?
What is the reason for that?
I'm sorry?
What is the reason for that?
What?
I'm so confused. Like, so when you take the average of the error, it's like the error of the different models, different like outcomes. But like, and then you're saying that like if you train all the data, the error is at least as good as the error you got by averaging each error. I'm not sure what is the reason.
Well, it's a fair question. So what I was saying you do is you take 95% of the data, you train a model, you test it, you get some error, then you take a different 95%, you test it again, and then you average this, okay? This average represents roughly the expected value you would get if you have any 95% of the data trained on 95% of the data, tested on some new data. The underlying assumption is that the more data you have in your training algorithm, the better the result would be. So if you have 100% instead of 95%, the argument is it could only be better. Of course, there could be pathological cases where it won't be. But I think it's a reasonable assumption. All right, let's come back to decision trees. In decision trees, how do we answer these questions? We answer this one. We answer this one saying minimize number of nodes. And now we're dealing with the third question, the search question. All right, now that I know that I want the smallest possible tree that agrees with my training data or that agrees as much as possible with training data, how do I find it? And this happened to be a very difficult problem in the case of trees. The number of possible trees to consider is exponentially large. In fact, it's doubly exponentially large. There's a very, very large number of decision trees. Of the trees, you don't have the ability to go over all of them. So we need to search them greedily. And the way we're going to do that is by starting from a root and growing the tree, trying to grow it as little as we can while making it as accurate as possible. We're going to start by drawing the root and putting all of our training data through the root. Remember that the training data consists of some attribute values and value, output value, label. In our case, the label is binary, so it's either a yes or a no. And if you look at the training data as a set, and you ask yourself, suppose I had to make a decision now on all the training data, the same decision, without making any distinctions, what decision would I make, and what would be my error rate? And if you had 9 cases of yes and 5 cases of no in your training data, you would take the majority decision if you had to, and you would be wrong 5 out of 14 of the time. This represents your uncertainty in the answer. You can think about it as related to the entropy of the label y. The entropy of the label y, when you start from 9 positive and 5 negatives, is the entropy of the binary distribution 9 over 14 and 5 over 14. We're now going to be using everything we learned about information theory. We're going to view the tree as an attempt to reduce the entropy of the label, either all the way to 0, or at least reduce it as much as possible, by consulting different attributes. Before we consulted the attributes, this is the entropy of the label. And now we're going to consider putting each one of the attributes here and splitting the data based on the value of the attribute. Assuming it's binary attribute, it's just to split. When we split the data, there would be some of the data will come this way, some of the data will come this way, and there will be conditional entropy here. Entropy of y, the label conditioned on the particular attribute, being 0. And here we would have entropy of y conditioned on this attribute being 1. We will take the weighted average of the two, and this would give us the conditional entropy of y given AI. Our goal is to minimize the remaining entropy in the label. To minimize this, over all AIs, which is the same as maximizing the mutual information between the label and AI. All this should look very familiar to you from your homework. So the algorithm we're going to use, it boils down to, at every node, find the one remaining attribute that has not been used, among all the ones that have not been used yet, find the remaining attribute that has the highest mutual information with the label. Label being y. So let's look at Tom Mitchell's example. In the book, Mitchell calls mutual information gain. And the formula he uses here you should recognize as the formula that we have used for mutual information. This weighted combination here is the conditional entropy. Now, when we did information theory, we started with probabilities, known probabilities. Here we don't know what the real probability of the different of the labels of the attributes are, but we have their empirical in the training data. So we're going to make the assumption, the approximation, we're going to use the empirical distribution as if they were the real probabilities. Okay? The real prevalence of positive and negative examples in future data may not be the same as it is in the training data, but it's probably close. The same is true for the distribution of the attribute values. The distribution of attribute values in future data may not be the same as it is, not be exactly the same as it is in the training data, but we use the training data as an approximation for it, as an estimate for it. So when I talk about entropy, conditional entropy, mutual information, implicitly what I'm talking about is the entropy, conditional entropy, mutual information of the empirical distribution. As long as the amount of training data is large, that's not a problem, it's a reasonable approximation. But once you start making decisions based on small amounts of data, a handful of data points, then it is a problem. Then it won't necessarily be the optimal decision. So let's look at this example. There's a total of 64 training examples. 29 of them are positive, 35 of them are negative. So the original entropy of the label is 29 over 64. It's the distribution, it's the entropy of 29 over 64, 35 over 64. How much is this? I'm sorry? A little bit less than 1 bit. It's not exactly balanced, but it's close to it. Now, we're considering, for simplicity, we're considering only 2 attributes here. In the real algorithm, we'll consider all the attributes that are available. We're considering attribute A1, attribute A2. If we split this node on attribute A1, we get this distribution of values. In one direction, we get a fairly imbalanced, mostly positive and some negatives. And the other one, we get mostly negatives and some positive. Here you have a slightly different distribution of values. Look how skewed this is. This is mostly positive, this is mostly negative. Is this a good thing or a bad thing? It's a good thing. What you're looking for is attributes that send as many of the positives in one direction as many of the negatives in the other direction. Right? Ideally, you would like one attribute that sends all positive to one direction, all negatives in the other direction. Then the tree is finished. You reduce the entropy to 0. So reducing the entropy to 0 corresponds to every leaf in the tree being what I call pure, being only negatives or only positives. And you can continue in this, well, let's first make this decision and then continue. Which one of these 2 should you use? Do you have a favorite? How many of you favor this one? Okay, how many favor this one? Okay, so it's not so clear from the numbers. You want it to be as skewed as possible. The rule that we use of maximizing the mutual information would help us answer it computationally, quantitatively. Switch to a different example. I apologize for that. So this is the example I started with. There's only 9 positive and 5 negatives. And the entropy is calculated as 0.94. Considering 2 attributes, they have either this split or that split. Notice that here the split seems to have done something not so great. It created a node that was balanced. And if it's balanced, it has one bit of information. So it actually increased the entropy in that node. The entropy here is higher than the entropy over there. If you remember from our discussion in information theory, that can happen. That once you're told something, your uncertainty can grow. The example with the glasses and the male-female, this is a case where it's happening. But what is guaranteed to be true is that the average of these should be lower or equal to one over there. So remember, gain means mutual information. You can plug in the values here for the conditional entropy and here for the probability of that attribute having this value. Calculate the mutual information and decide which one to use. Once you chose one attribute, you fix it, you allow all your training data to flow through that question and go to the two nodes, and now you repeat the algorithm recursively in each one of the children. So it's a recursive algorithm, and at every point in the recursion, you have some amount of training data, you have some number of attributes that have not been used yet, and you simply apply this to them. The difference is that in the root, the solution looks like this, but further down the tree, the solution would look mutual information between Y and AI conditioned on all the A's, all attributes in the path. Specifically not on attributes equals values in a path. So if you build a tree that looks like this, and you're about to split this node, this is a false, this is a true, this is true. If you're about to split this node, then the equation you would be looking at would be conditioned on whatever attribute sits here being false and whatever attributes, call it A1 equals false, and call it 5, A5 equals true, and A9 equals true. So this is your conditioning here. Very simple algorithm if you can write recursion. Right? The whole algorithm is like this big. When does the algorithm stop? When do you stop the process?
Zero or you run out of attributes.
When either the conditional entropy is 0, so there's nothing to improve, or you ran out of attributes. Can it happen that you would run out of attributes before the entropy is 0? Under what conditions? I'm sorry?
You couldn't do perfect classification based on training data.
I missed the beginning part.
You couldn't do perfect classification.
If you could not do perfect classification based on your initial training data, when would that happen? When you have multiple training examples that have identical attribute values but different label. And this could happen either if you have noise in the data, or if, namely error in the data, either in the attributes or in the labels, or if the function is intrinsically non-deterministic. It's not an error, it's just gave you different values at different times. Assuming this is not the case, the algorithm will terminate when all the leaves are pure. And now you have the tree that you wanted. Well, now you have a tree that is completely agrees with the training data? And is it the smallest possible tree that agrees with the training data? Are you guaranteed that you got now the smallest possible tree that agrees with the training data? No. The answer is no. What we used here, the mutual information, is a heuristic. It was a greedy approach. We made the optimal decision in terms of one step. It was one step optimal, but it was not globally optimal necessarily. So it is possible that there are other trees that fully agree with the training data that have fewer nodes, but we haven't found them. Can you think of an example where this might actually happen? Think back to information theory. One of the issues we discussed with mutual information, or with information being additive, sub-additive, super-additive. Suppose the real answer depended on an XOR of two variables. Then the value of each one of these variables to the label will not appear to be very high. The mutual information between any one of these two variables and the label will be quite low. And therefore they're not likely to be chosen early on. So this algorithm chooses attributes based on their apparent short-term value in reducing entropy. It doesn't have the ability to look ahead to see that X7 is not helpful, but when you combine it with X19, all of a sudden they are. Can we solve this problem? Can you modify the algorithm to be able to detect this kind of pairwise usefulness? Suppose you suspect that the answer to your problem is really an XOR of two variables. How can you modify this algorithm to find it?
Well, can we say something like a bin size and so they are unable to look a few steps ahead and try to...
Look ahead. Yeah, you can do 2 steps ahead. One way of doing that would be to modify this to find the pair that maximizes the mutual information between the label and that pair. Conditioned on the path. Now you argmax over I and j. So instead of searching one attribute at a time, you can search 2 attributes at a time. Did we solve the problem? No? Why not?
What if it's 3 things that need to be concatenated?
So we solved part of the problem, but not the full problem. What if the answer depends on the XOR of 3 things, on a combination of 3 attributes? Then this will miss it. Well, then let's make it IJK. Why not? What's wrong with that?
What's the sequence of I, J, and K?
What is the sequence?
Of I, J, and K.
All possible triplets.
I mean the tree, which is a high, which is a...
Which is higher in the tree? That's a good question. I don't think it matters. Once you decide that you're going to use all 3 of them, then you build a full tree of I and then J and then K, or in any other order. You're still left with 8 nodes at the bottom that are fully differentiated by the values of I, J, and K, assuming they're binary. So first of all, we have a computational problem here. When we did the original maximization. This has to be done as many times as there are attributes. Let's say 100 attributes. When we did I and j, this has to be done as many as there are pairs of attributes, which is 100 choose 2, which is about 5,000. If we're going to do it of all triplets, now we're talking about 100 choose 3, which is on the order of 200,000. So a lot more computation. But that's not the only problem we have. I told you I'm willing to give you infinite computing power for the purpose of this course. I'm not so concerned about computation. Go ahead.
I was thinking that, like, if you're gonna check two tuple and three tuple, you have to check all the tuples.
Right. You have to check all the tuples, right. So checking all the tuples would be how many times we do this calculation?
2 to the 100.
2 to the 100, exponential number. I don't know if I want to give you that much computation. But suppose I even wanted to give you that much computation. Suppose you had infinite computing power. You are now removing completely your bias. Because if you can check mutual information with any subset of the inputs, you basically can express any tree with a single node, or with a single, you're basically considering all possible trees. So you removed your bias. All right, let me go over some of the slides. You're going to get a assignment today that you'll have to implement. So this is a good example to be aware of. In this example, the high level of the tree was chosen to be the attribute outlook, and then we repeat the process, the recursive step on each one of the children. The middle child does not need to be split any further, so we can put the label there. All right, this is one I wanted to show you. This is tracing the accuracy of the decision tree as it was tested on test data, on separate data, as a function of the number of nodes in the tree. So imagine you start building a tree using this recursive algorithm. Once you split on the first node, you have a tree of size 1 node. You stop at that point and you measure how well this tree does on test data, and you also measure how well it does on your training data. Okay, so two sets, the data used for splitting the tree. And you keep going, increasing the tree size one step at a time using this recursive algorithm. And what you find, accuracy is the opposite of error rate, so it's 1 minus that is the error rate. What you find is a very, very typical set of curves that you will see over and over again in many machine learning setups for training set error and test set error. What you would typically find is that training set error will continue to go down, namely the accuracy will continue to improve. This is almost guaranteed to be the case. It's almost guaranteed it will never go down. It's not completely guaranteed in this case, but practically, as you build a more and more elaborate model, it will almost always do better on your training data because it is designed to improve performance on your training data. It's directly optimized on your training data. If you track what happens on test data, you will find that it also, performance on test data also improves, but only up to a point. And at some point it levels off, and then it starts actually going down. Performance goes down, accuracy goes down, namely error rate goes up. This is the point here. The place where these two curves start splitting in their behavior is the onset of overfitting. So this, what you're looking at, is almost a textbook, well, it is a textbook definition of overfitting. Overfitting by definition, you can define it many different ways, is fitting your training data better than you're going to fit future data, which here is represented by test data. Why does overfitting happen? You can think of trying to explain your data as consisting of two parts. When you try to find an explanation in your hypothesis space for your data, there are two ways or two components to that. One is you believe that there's some regularity in the data. There's some underlying relatively simple explanation for why the label is one way in some cases and different way in other cases. And your goal is to find that regularity. This is the goal of machine learning, finding a regularity in data so you can predict the future. But once you're exposed to a particular training set, you can also perform better on this training set by kind of memorizing what's in the training set. If you don't find regularity, you can fall back on memorizing. Or if you find some regularity, you can still try to memorize the exceptions to that regularity. And anytime you train a model, you try to fit a model or to find a member of the hypothesis space, what you're finding is something that strikes a balance between capturing irregularity and memorizing the training data to the extent it can. When you go to test data, the regularity carries over, the memorizing part doesn't. Which means that you should prefer methods that don't have much memorization power. Here's an example. You're trying to train me on remembering some sequences. You give me the beginning of the sequence and I have to memorize the continuation. If I figured out the rule that you use, all I have to remember is that rule, and then when you test me on new sequences, I can tell you the continuation very successfully. If I fail to find the regularity, what do? I memorize. I memorize what you told me, in each case, what the continuation is. I go to test data and I'm helpless. I'm not useful. I'm better off if I don't have good memory. Not having good memory is useful here because it will force me to find some regularity. The analogy in our case to having good memory is having large expressive power. If you don't have much hard bias, if you can express a lot of things, you can kind of memorize the training data to some extent. And that will not generalize. Which means that the larger the tree, the more memorization power it has, the more poorly it will perform on test data. Another way of solving the memorization problem is increasing the fixed amount of memorization for a fixed amount of expressive power. If you just overwhelm me with examples, I could not remember all of them. I will again be forced to find regularities if I can. So what you want to make sure is that the amount of training data you have doesn't fit into the rote memorization of your algorithm. That's what overfitting is about. Overfitting happens when your algorithm settles on something that is not completely the regularity you were looking for. It includes some idiosyncratic elements of the data. It basically memorizes specific things that happen in this training data that are not likely to happen elsewhere. That was a question or a comment. Yes?
Yeah, so I can think of cases where, for the most part, it's important to have regularity, and then there are specific cases where you have to memorize. Like in the English language, there's a bunch of rules, and then there's just some times where the rules just break down, and it just happens this way because that's the way it happens.
Right.
So how do you get to those really crucial memorization points without missing the regularity?
What a wonderful question, and I have not gotten it yet, which is rare. Usually, same questions come up. So let me repeat the question. There are many domains where there is strong regularity and yet there are some clear exceptions. And natural language is a wonderful example of that. You know, there are many rules that, and depending on which natural language, English happens to have more exceptions than other languages, but all languages have exceptions. How do you deal with that situation where you still want to learn regularity and you have the exceptions? So here's my on my feet answer. If the exceptions have some rule or rhyme to them, then you can try to learn that as well. But underlying your question, I assume, is the assumption that the exceptions are really truly random, or really there's no way of combining them. If they're truly random, the only way you know their exception is by being taught it, by maybe making the mistake and being corrected. So what I would do is I would start with an algorithm that has a strong bias, that looks for strong regularity, but I will allow in my learning process that if I'm corrected that I made a mistake, I will allow the possibility that this is a special rule. I assume this is what we all do when we learn language. Right? We overgeneralize the past tense of verbs, and then we're corrected when I didn't seed, I saw, right? A young child might say, I seed it yesterday, and the parent might correct them, no, you say, I saw it yesterday, and they realize an exception, yeah?
So is there maybe some way to keep track of all your special rules as you're learning, and then keep trying to generalize your special rules? Like maybe you pick up on 10 different special rules and you're like, oh, there's the pattern.
Right.
Fit to that.
Wonderful suggestion. So the suggestion is keep track of your special rules and then try to generalize them. You need to assume that there is some generalization to those, right? And what it is based on, you need to bring another. So it's a learning problem on top of a learning problem, right? But yeah, that sounds like a reasonable approach to me. Okay, what do we do knowing that overfitting is going to set in at some point? Do we keep growing the tree? Oh, notice, by the way, that even performance on the training data does not reach 100% at this point, after 90 nodes. Okay? So you may need to go a lot further to fully resolve all the training examples. So one modification we're going to make to algorithm is we're not going to necessarily go until all the nodes are pure, until the entropy is completely zero. We're going to stop at some point. And when we stop, it could be that some of the nodes have a mixture of positive and negative labels, in which case we will decide that the tree gives the label of the majority in that node. So you take a vote there. Or if you want to be really sophisticated about it, you can give a hedged answer, 60-40. But for simplicity, let's say that you give the majority label there, and that's what the error rate of these trees, how the error rate of these trees are measured. Because if you build a tree, say, up to here, the tree didn't fully classify all of the training examples, so we need a rule for, it didn't fully resolve all the nodes, we need a rule for how to label each leaf, and the rule is majority. Now we need to give our answer to whoever gave us this task. What should you give them? Which tree would you choose? How many nodes in your tree? You've now produced close to 100 trees, right? One for each number of nodes. Which one is the best one to use? The one that does the best job on the training data? No. The one that does the best job on the test data? And that means somewhere between here and here, right? Where between here and here? So this is between 10 and 20 nodes. Do you prefer the one with 10, 15, 16, 17, 20? 10. Why 10? Occam's razor. They're all equally good. Choose the simpler one. In fact, I would argue that even if this one was slightly lower, I might still be tempted to go further, depending on, again, it's the trade-off between degree of fit and simplicity. A couple peculiarities about trees. Yes.
I want to ask a question of going back.
Okay.
So previously we said it's not feasible that we just like give off the possible combination of JK. So what actually is the solution to this problem without?
So going back to the problem of the answer depending on an XOR of multiple variables, the question is, we said that it's not feasible to test all combinations of attributes. So what is the solution? First of all, let me qualify what we mean by it's not feasible. It is computationally not feasible. We would need 2 to the 100 tests. But if we were able to do it computationally, we would have a bigger problem. It's not a viable way to go. So the answer is there is no solution to that problem unless you believe in advance that you bring in a different bias, a different assumption in, that the solution is always an XOR of some number of variables. And then trees would not be the right solution for that. So trees are suitable for problems where you believe that the answer depends on a small number of attributes. Right? Otherwise, don't use trees. They're not the thing to do. If you use a tree, you're hoping for a small tree typically, and a small tree means you're only consulting the values of a small number of attributes. Some problems are reasonable for that, some are not. So let me give you some examples. You all know the school rankings, the US World News Report school rankings, right? College rankings, right? I'm sure you know it, that's why you're here. Now, they keep their formula of the ranking, I think, secret, I'm not sure. I certainly don't know the formula, but I know that they send surveys to schools and ask them a lot of questions about how many students and how many professors, how many publications, how much money, how many classes, how many degrees. You know, they have lots of questions for which the answers are numerical or categorical. And they take all this data and they somehow produce a score that helps rank you. Now, do you think if you were trying to reverse engineer their process, if they don't tell you how they do it, but they show you all the attributes and they show you the score at the end, and let's say the score is categorical, A, B, C, D, E, F, or something like that, would you try to use a decision tree to learn their formula, to learn their mechanism? Why not? Well, but okay, you can, a decision tree can work with lots of attributes. You do this loop over all the attributes. So 100, 200, that's fine.
I think the biggest problem is that we can hardly give a label in advance to all the training data.
Oh, they give you the labels. They give you, the US News and World Report gave you all of their attributes values for all the universities and the label. Let's say the label is very simple, it's binary. It's either a great school or a terrible school. Okay? Very simple. So it's binary classification. Yeah? The size of the? The range. The rating. But I'm now saying, let's say there's just binary rating.
How to rank the schools.
Yeah, let's say what you're trying to do is decide whether you're in the top half of the ranking or the bottom half of the ranking, okay? You're trying to figure that out. Okay, you got a lot of training data from US News and World Report. It consists of lots of universities and all of their values, you know, their 200 attribute values, and at the end whether they were in the top half or the bottom half of their ranking. And now there's a new university that gives you their numbers, and you need to basically reverse engineer the formula that US News and World Report used. Will you use a decision tree for it? Why not?
Well, they're using all of the attributes.
Because they are likely to be using all of the attributes. Thank you. I just told you guys 2 minutes ago that decision trees are particularly suitable when you believe the answer depends on a small number of attributes, right? Because you're trying to grow a small tree that consults only a small number of attributes. We're assuming that Use News and World Report uses all the attributes that we gave them. They weigh some of them more, they weigh some of them less, but they use all of them, otherwise why would they ask for them? All right, you can argue with me, but it is a reasonable assumption that they use all of them. That the answer depends on all of them in some way. That they all play a role, a meaningful role, a significant role. Or at least that a large number of them plays a significant role. If that's the case, you don't want a decision tree. You don't want a tree. What might you use? What is the most likely thing that they do?
Linear regression.
Linear regression. The most likely thing that they do is weighted combination, and you need to find the weights. That's linear regression. All right, here's another example. A certain country, say the country specifically Brazil, discovers all of a sudden a huge spike in the number of babies born with brain damage, microcephaly. This happened all of a sudden, and they suspect a whole bunch of things. They suspect the environment, global warming, mosquitoes, viruses. They have a collection of 100 variables, and how they appeared before this outbreak happened and what their values were after the outbreak happened, and just a month before, 6 months before, a year before. 100 different variables that could be related. Some of them are environmental, some of them are biological, some of them are nutritional, some of them are educational, political, social, lots of things. You're trying to figure out from the training data what cause was. Would you use a decision tree? Why? Why?
It probably depends on a select number of variables.
Because the answer probably depends on only a small number of attributes. Why? Because you knew I would give one positive and one negative example. Yeah?
In this case, the people who came up with the set of possible attributes, they didn't know the exact, method of choosing whether or not the baby would be born with brain damage. It was kind of a speculation that they could be.
That's a very, very important observation and discussion. The attributes were generated by people who did not know the answer. So they did not know what's relevant, what's not relevant. So it's likely to contain many irrelevant attributes. Whereas in the case of US World and News Report, you were given the attributes by US World and News Report. So, another reason is the sudden spike. Because something happened all of a sudden, and that's a true story, as you probably know, because it happened all of a sudden, it is not likely to be that multiple unrelated attributes change the value at the same time all of a sudden. It could be, but it's far less likely. It's far less likely that there was a drought just the year before, and there was an infestation of mice just the year after, and this and that. Sometimes they talk about the perfect storm, the confluence of multiple unlikely events that all happen at the same time. It does happen every now and then. But most likely, most of the time, it's not a combination of 6 unusual things that happen at the same time. It's 1, maybe 2. Okay? Think decision trees. If you're trying to find a small number of attributes to explain from a large set of potential attributes, think decision trees. If you know that all the attributes are relevant, then decision trees are not the right solution for you. All right, you have an assignment. It will be out today. It will be due a week from now. Let me just give you a little heads up. We're going to talk about linear regression and linear learning in the next 2 lectures. Maybe manage to touch on neural networks before the midterm, maybe not. Midterm is next Thursday evening at Meconomy, right? At Meconomy. All right, and it will include everything we learn up to that point. Thank you.